This video will introduce transient simulations using ModFlow by evaluating the heads in an aquifer next to a stream when the stream experiences a sudden change in stage due to a flood pulse. So we can see what we have in mind here. If we look down at this lower picture, here's a stream that's just flowing under ambient, perhaps base flow conditions, and then we get some rainfall up in the watershed, and the stage rises by a few feet, and we have a channel that's filled with water here. And we could imagine then the alluvial aquifer back underlying this floodplain would see this change in stage, and there would be a change in head that propagates from the stream into the aquifer, propagates laterally. This is sometimes called a bank flow storage. It affects the stage of the stream, and it also causes fluctuations of a water level in the aquifer. So we'll come up with a conceptual model by taking cross-section through the stream like this, and then we'll look at it in a mirror image, and here's the stream, and here's the aquifer. And we're looking at it in cross-section, so this is the hydraulic head, and we're imagining that initially the stage of the stream was right here, equal to the hydraulic head in the aquifer, and it's increased as a result of this flood pulse by this much. So that's the change in the head, and then this change in head would propagate into the stream or into the aquifer with time. So we'd have a wave that progresses into the aquifer with time, and that's what we're going to be interested in simulating. So when we set up the model, this is what it's going to look like in plan view. It'll be long in this direction and fairly narrow. We'll really only be interested in changes that are in this direction. The model will not have any variation in this direction, so really it will be just one-dimensional, although we'll set it up as a 2D model. The boundary conditions are no flow on these three sides, and here we'll specify the hydraulic head. The initial head is equal to 50 feet, and we'll specify that the hydraulic head along this boundary is equal to 60 feet. That will be the flood pulse, and it'll be a change of stage of 10 feet. These are the dimensions. It's 10,000 feet in this direction, 100 feet in that direction, and it'll be 70 feet thick. We'll just use one layer in the grid for this model. Here's the initial head at the boundary, and these are the properties: the hydraulic conductivity, the specific yield of 0.1, a specific storage of 10 to the minus 5 per foot. The head changes 10 feet. That's a pretty good size flood pulse, but within reason, I think. And what we're going to be interested in is how far does this head change propagate into the aquifer in one day? What is the effect of whether the aquifer is confined or unconfined to the distance of propagation? And what is the effect of a pulse when the water level rises for a day and then falls back to equilibrium? What does that look like? Okay, so let's go take a look at the model. Okay, so to set the model up, we'll use the grid frame to build a grid. These are the dimensions that we specified. So we'll use the grid frame and map to a 3D grid, and we'll make it 300 by 10 by 1. And so there's the grid. It's really just a 2D grid, one layer, and the column and row. This is looking down on the grid. And then here's the conceptual model. This is the recharge, 0 for now. Hydraulic conductivity over the whole area is 50 feet per day, and the anisotropies are both 1. The river is constant head boundary on the left side. You can see it over there. And it's specified head, and we use the layer range. And it's going to be a auto-signed BC to 1 cell. And we're going to use this transient setup in a minute, but right now we're just going to have it be a constant head of 60. And then we also need to specify the specific storage and the specific yield. So we can identify the parameters there, and then in the attribute table, we'll specify their values. 10 to the minus 5 for the specific storage, 10 to the minus 5 per foot, and 0.1 for the specific yield. And then also put in some points that we'll use as reference points. So there's the grid, and we'll add mod flow. And we're going to switch the starting heads. The default is that they're at the top of the grid at 70. We're going to start them at 50. And we're going to switch the model to transient. We're going to set up the stress periods. We're going to have 1 day with 50 time steps. So that allows us to set up and run a transient model. Now we'll map it to mod flow and run it. And we see the green bar for the simulations, and we can see here that it has converged. It's run successfully, and we can see that for each time step, for each time step, it runs typically 2 iterations. And now we go to the heads and take a look at the results. We see that these are heads at different time steps. And we can see that was just the map view. This is the cross-section view. And we can see the profile of the heads changing with time. So that analysis was for an unconfined aquifer. And you can see it was only influencing a few hundred feet from the river. So we're going to change it now to confined and rerun it. So this is confined. This is at early times, 0.12 days, 0.2. And then here is after 1 day. You can see after 1 day, it's the pressure or the head change has propagated over more than half of this 10,000 foot wide aquifer. When it was unconfined, it only went about 1/10 of that. And the reason for this is because when it's unconfined, the hydraulic diffusivity is governed by the specific yield, and when it's confined, it's governed by the specific storage. And that changes the rate at which the pressure diffuses by quite a lot. Now I want to show you how to get some plots of the time series of pressure at these points. So I've identified these points, and I like to use I like to name the points with as the name of the grid block that they're in. So you go and select the grid block and find out what the number of the grid block is. So here the block is selected. I go to properties. A couple of ways you can do it. There's the cell ID number. It looks like 1239. It's pretty small on my screen. And then we go and we select the point, and we change the name of the point to the grid block. We also see we can get the X coordinate of that point, and that'll be good because that's what we're going to need to plot up the analytical solution. So we're going to do this other point here. We get the grid block number, and notice the cell ID. Notice down there in the lower left hand corner it showed up, and now we'll put the cell ID there, and it shows up as the name of the point. We'll switch this one over as well. And then there are the different names and the X values that give the locations. Those X values are the distance from the stream. So what we want to do is get the hydraulic head as a function of time at these different locations. So after we set them up with names, this one, the name is a little bit different, point, whatever the cell ID number is, and I'll show you where that will come in. It just also gives us a nice convenient way to put labels on the map that shows the layout of the model. Okay, so now we'll zoom out a bit so we can see the model, and we're going to select these points. So we use the grid tool and select individual cells at the locations of these points. So if I select the cell and then press that plot tool, you can see that I get the hydraulic head as a function of time. And now if I select all of these cells, go to the plot tool and select active data sets, that's the hydraulic head for all 4 of those different points. And you can see the cell IDs listed up at the top of the page. I can export the data. This exports the data to a file on the clipboard, or data set on the clipboard, and I can paste it into Excel. You can see the cell ID on the right. There's a column there that's not needed, so I'm just going to erase it. The cell IDs on the left. The column B is the time, and column C is the head. And so I'm just going to put a label in there just to make it a little bit easier to follow. There's the time in days, and there's the head in feet. All 4 data sets are in these columns. There's the next one. You can see the cell ID has changed. So I'm just going to go in and copy that, cut it out of that block, and then paste it up at the top. I'm going to leave a blank column there. I'll show you why in just a second. I'm going to do that same thing for these other 2 data sets. Okay, so there's the data in Excel, and now we can plot it up. And so we just do the conventional plotting approach for Excel, and there's the head as a function of time at that point. Okay, so now what I want to do is compare the results that we've gotten to the analytical solution. So I'm going to put in the parameters. These are the parameters that we used in the model. Hydraulic conductivity and specific storage. Remember, this is the confined model. And so the hydraulic diffusivity will be the ratio of the hydraulic conductivity and the specific storage. And those units will be feet squared per day. Okay, so now we want to take a look at the analytical solution. This is the analytical solution for the heads due to a sudden change in head on a boundary. It's this error function solution. H0 is the change in head, X is the distance, T is time, and D is the hydraulic diffusivity. So we'll take that formula and put it into Excel. And there it is. 50 is the initial head, so we add that on. H0 or delta H is 10. And there's the error function. There's the X value is in D4. And then you can see the hydraulic diffusivity and the time are referred to. So I write that formula in there and then use a similar formula but with slightly different cell references. And I copy that down for the next location. And same with this location. And notice those X values for the cells, that 30, 50 in column L. That was what I determined from the location of that point when we were setting up the model previously. And so there's the plots. The lines are the analytical solution, the error function solution, and the points are from our numerical model. So those are pretty similar. And so it looks like we've been able to verify this solution with the analytical solution. We verified our numerical model with this analytical solution. So that gives us some confidence that the numerical model is right and that we have an understanding about what's happening. And so this is how I set up that model. You should try to export the data and set up a similar plot, although you can certainly use different locations for the points. Okay, so now I want to go and simulate a pulse where the head falls after 1 day. So I'm going to add another stress period. The first stress period is 1 day when the head is high, and then the stress changes because the head drops between day 1 and day 5. So that's why we have 2 stress periods, 2 different kinds of stresses on the system. And I have to change the head in the river, and so I'm going to go to the transient boundary condition, and I'm going to put in day 0, and day 0 is head of 60. That's pretty much what we just were using. Day 1 also head of 60, day 1 head of 50, and day 5 head of 50. And that gives us a head that looks like that on the boundary. So then I can save that. And then for this next node, I can use the same, I can just import that file. That way I don't have to remember all those numbers. I can just import it to make sure that it's exactly the same. Okay, so now I can map this and we'll run this. And this will be for a 1 day long flood pulse followed by 4 days where the stage has returned to the ambient conditions and the heads in aquifer can equilibrate after the flood. So this is what it looks like. There's the flood migrating out. 0.7 days, there's right at the end of the flood. And then there you can see the head drops and it propagates out for 2 days, 2.5, and it equilibrates back out. Okay, so there's a flood pulse that propagates through an aquifer, and the aquifer returns to equilibrium. So we can go back to our points here and select the cells. And we're going to select all 4 of those cells that correspond to those points, and then go to active data set time series. And this is what the heads look like now. You can see they rise, and then after the flood is over and the head drops back, the heads drop back as well. And we get this fluctuating head in the aquifer. Okay, so let's take a look at what that flood pulse, that day-long flood pulse, would look like if the aquifer was unconfined. So we switched the aquifer type, made it convertible, and because the starting heads are below the top of the grid layer, then this will behave as if it's unconfined, and we can see that we've got a much smaller flood pulse this time. So it's only going out. Remember, the other one went more than halfway across the aquifer. This one is only going out, I think that's just a few hundred feet. Now you can see, if we go just time step by time step, you can see what this pulse looks like. It's decaying out and propagating out, and then returning back to equilibrium after, I don't know, it'll equilibrate out after about 3 days, I think. So that's about as far as the pulse gets. And let's see, it's hard for me to read that. I guess that's about 500 feet. So maybe roughly 200 yards into the aquifer. So much shorter distance of propagation for the unconfined. Now I'm going to show you how to make an animation of this. There's an animation tool. If you go back, you can see how I selected this animation tool. Go and set it up like I'm showing you here. Put that display clock on, and then let it run. And if you set this up so that it requires a lot of time steps, it may take quite a while to run. This one, I only have the time intervals every 1/10 of a day, and it goes from the beginning to 3 days. So it's going to be 30 images, and this is what it looks like. I have some kind of peculiar black flashing up there, I think because of my graphics card in my computer. Hopefully yours looks better when you try it. Animation can be quite nice to visualize transient models. Okay, so let me show you how to make a cross section. Go to the file data set, and in 3D data sets, select the hydraulic heads, and then you can select the row and paste it into Excel. So there's the hydraulic heads at the time that we selected. And then this is going to be the X value of the grid block. So I'm just going to, since these are evenly spaced grid blocks, there are 300 of them over 10,000 feet, then I can just calculate what the grid blocks are and copy that over. And then I can select these data and make a plot. This will allow me to plot the hydraulic head as a function of distance at a particular time. And there it is. There's the time profile of hydraulic head. This is right at the end of the high water. And so we might want to take a look at what this profile is like a little bit later in time. So we can advance the time. So there's the time. This is now 1.24, and we'll select a row in the data set and copy it. Paste it in this row in Excel, and then we'll add this to the plot. Okay, so there's what the profile of the hydraulic head looks like shortly after the head drops. I think this is 1.24 days.